So scary when that beep happens. Okay, so here we go. I want us to tackle number 6 to begin with, okay? So everybody look at it here. What is the definition of curvature? And I'm going to throw that question to, oops, I forgot my cards. Let's go with Keenan. What's curvature?
How quickly the tangent vector turns.
Yeah, good job. How quickly the tangent vector turns. So could you write it as the magnitude of something? Do you remember how I said there's a definition that's not useful, but it's conceptually correct? Can you do it? D over, it's a derivative. It's d something, d something. Yeah, you can get help. I don't care.
I think
Yeah, it's dt ds, right? So it's the rate of change of the unit tangent vector with respect to arc length. And we can reparameterize with respect to arc length. Good. Okay, B. Let's go with Chris on this one. Write a formula for curvature in terms of r prime and big T prime.
the magnitude of big T prime over the magnitude of r prime.
Nice. So this one is slightly more convenient than this one because this one doesn't involve parametrizing in terms of arc length. Okay, so you can use that one. Good, thanks, Chris. And let's go with Amanda. Let's do C together. Write a formula for curvature in terms of r prime and r double prime.
The magnitude of double prime of x or f of x double prime.
Okay, so you're thinking of the one that's questioned. Write a formula for the curvature of a plane curve with equation y equals f of x. You can get help at your table if you want. Does anybody have it? Got it? Go ahead.
Magnitude of r prime plus r double prime over the cube of the magnitude of r prime.
Good job. Would you like me to ask you to derive that on the test? Yes, Nathan wants me to. I think I heard you say make the test harder and then curve it more. Did you say that? Okay. Now listen, I really admire you for saying that because I kind of agree with you. I think it's kind of cool. I think it's kind of cool to decimate you on a test.
Absolutely.
And then just be like, well, a 40's an A, you know?
Math team.
Yeah, like math team, exactly. That is honestly when you're doing real mathematical work. Now, don't worry, I won't do that, okay? But it's kind of interesting. Okay, D. Let's go with Peter. What's D? Write a formula for the curvature of a plane curve with equation y equals f of x. And of course, you can cheat off the formula sheet if you want. I just want to review it.
So it's one where it's like the second derivative of f of x, and then you take the magnitude of that.
So it's actually not magnitude, though, is it? What is it? This is absolute value because what kind of function is f? It's a scalar function, not a vector function. Okay. Now at the bottom, what's that?
Then that is 1 plus the derivative of f of x squared.
Good job.
And then all of that, all of the bottom is to the 1.5 power.
Good job. 3 halves. Perfect. Okay, so I do want you to be aware of what each of these things means. In practice, you're going to use this one or this one, right? Those two, though, I want you to know that that's kind of a conceptual definition. That would be a nice question to just start the quiz with. What's a conceptual, not the quiz, but the exam. What's a conceptual definition of curvature? Would be that. Okay, 7a. Write formulas for the unit normal and binormal vectors of a smooth space curve R. Okay, let's go with Raphael on that one.
So for unit normal,
This implies that I don't know your name, so I don't want to give you that. Go ahead. Unit normal.
so for unit normal, you do the r common t over the magnitude of r prime.
Think again. Unit normal is not R.
Oh,
is it
sorry,
R?
sorry, yeah. The tangent
There you go.
over the magnitude, or
Yep. Over the magnitude of that. So it's big T prime over the magnitude of big T prime. That's the unit normal vector. Good. Okay. B, what is the normal plane of a curve at a point? What is the oscillating plane? Oh, wait, we didn't do binormal.
So then just do the cross part of t prime with, or not prime, sorry, with
T cross N. Yeah. The way I remember it is to say in my mind, Big Ten network. Okay? because I can't remember if it's N cross T or T cross N. So big 10 network. That's the order it goes. Okay, B. What is the normal plane of a curve at a point? What is the oscillating plane? So let's have someone tell me what the normal plane is at a point. And let's just go with a random person. Ninja.
Normal plane is the plane that is perpendicular to the curve.
Good. So the normal vector, the ABC vector, is what?
The tangent vector.
Is the tangent vector. Very good. Okay. So the normal plane uses the tangent vector or some scalar multiple. Oh, did you guys notice I did the homework solutions in one take? I said it in the end, I did it, yeah. I was really impressed with myself. I was feeling good about that. Although I have to confess, I've started, since I have dual monitors, I've started keeping the solutions up on one monitor so that you probably heard me say that. Oh, let me check the solutions to make sure that's true. That way I know that I'm not making mistakes. But I promise I'm working it out for real, okay? All right, so that's that. So, or some scalar multiple. So what's the oscillating plane?
The oscillating plane is the plane that has the vector for the plane is, I believe it's N cross B.
Yeah, it's well really either because it's the vector is B. We're going to use B as the ABC. So it's the kissing plane. It's the plane that just grazes the curve there. Okay. Are we ready to do 8A yet, or do we not know that? Yeah.
What's the binaural vector?
So the binormal vector is orthogonal to both tangent and normal. To get a picture of it, it's in your text. There's a nice picture of kind of what it looks like in relation to the curve. But if you just Google it, the Wikipedia page has a pretty decent image of it. So, there.
Oh yeah, the kissing.
Yeah, right. So, see, look at this. If we're spinning around here and we come to this point, unit tangents in the direction of motion, unit normal points are orthogonal to that, but kind of like toward the direction of curvature. You know what I mean? And then binormal just takes the cross product of those two, to be pointing out toward us. The plane that's showing here is the oscillating plane. Okay. Thumbs up. Question? No. Okay. Okay. We are never going to do Kepler's laws. You can scratch that. Go ahead.
Is there any thing that's like the third thing?
The other one, I don't know the name of it. I think it's part of the story, but I don't know the name.
I'm still confused on why the normal vector is derived from the tangent. I mean,
Oh, you asked about that, didn't you? Like, why is it related to T prime?
yeah.
Let me grab a textbook. Do one of you have one, or do I need to speak back to the
website.
Oh, yeah, wait. I can just pull it up on the screen. Okay. Let me find it for you. It's in here, and it's a few pages into this section where it explains that. It's right here. Okay. So let's read this paragraph together. At a given point on a smooth curve R of T, there are many vectors that are orthogonal to the unit tangent vector. Does that make sense visually if I do it with a curve?
Yeah.
Like, if the unit tangent vector is my marker, think of all the vectors that are orthogonal to it. All of these, right? And we're interested in one of them. Can you see that, Joshua? Do you understand what I'm doing? Right? Like, if we've got unit tangent, and then all of these vectors are orthogonal to it. Okay? So then it says, we single out one by observing that because the magnitude of big T is 1 for all T, we have big T dot big T prime equals 0. And they say by example 4 in section 13.2. Okay, I did that example with you guys. That's the one where we showed that when something has a constant length, it and its derivative are orthogonal. You have it in your notes somewhere. So that's the reason, because this has constant length, the derivative of itself and its dot product of itself and its derivative are 0. So T prime is orthogonal to T. Note that T prime itself is not a unit vector, but at any point where curvature does not equal 0, we can define the principal unit normal vector, N of T, or simply the unit normal, as this. So it's because of a theorem that I proved earlier that they're orthogonal. What do you think of that?
I mean, I guess I can.
Is that okay? So that's why that's true. If you want to see the proof of it, you can go back to the previous section and see example 4. It's right here. Show that if the magnitude of R is a constant, then R prime is orthogonal to R for all t. So we're just applying that rule to big T. Is that okay?
Yeah.
Okay. All right. Where were we? On question number 8. How do you find the velocity, speed, and acceleration of a particle that moves along a space curve? All right, let's talk to Gretchen. How do you do 8A?
Let's see.
So given RT, that's given. How do we find velocity, acceleration, and speed?
It's speed just or velocity just do the derivative.
Good. So v of t equals the derivative of r prime. And acceleration?
Speed would be the magnitude of that.
Yep, good. So speed, which is sometimes we call it ds dt, is the magnitude of r prime of t. And then a of t is
The derivative of velocity.
that one, right? R double prime or v prime. Good. And then b we haven't learned yet, right? The acceleration in terms of its tangential and normal components. We'll learn that soon. Kepler's laws we're never going to do.
Is that the oval in the area that
The amount
planet covers?
Yes.
equals the same.
It's right here. It's if you, I don't know if any of you'd ever do this, but they do a 2-page kind of thing on it right here on planetary motion that starts with some stuff from physics, right? At least I vaguely remember this from physics. So you can explore if you want, but we're not going to cover it here. Okay, let's do the true false. I think we left off. Let's do 8. Okay, it's on the board. All right, so let's take Mike. What is 8 true or false? False. Good. It's t cross n. Good. 9. Suppose f is twice continuously differentiable. At an inflection point of the curve of y equals f of x, the curvature is 0. What the heck? Is that true? I don't even know. Wait, I gotta think about that.
The inflection point is where the double derivative is false. It's 0. And anything crossing the 0 factor.
That's true.
Must be 0.
Look at the formula, right? At an inflection point, f double prime is 0, so curvature would be 0. That's true. All right, good. Nobody had to answer that one. If k of t equals 0 for all t, the curve is a straight line. It sounds right. Can we think of an exception? Yeah, I knew you'd come up with an exception.
If it's absolute value, it wouldn't
Oh, there would be no curvature at the origin for absolute value?
I don't
Then I would say this condition doesn't hold then though, right? He's talking just about the absolute value function, right? So at t equals 0, there is no curvature, so we would say that this original statement doesn't hold. It sounds true to me.
You can actually prove it with what we did for the previous problem.
Exactly.
If y equals f of x,
Oh, sure, yeah.
like, because it has to be an inflection point, that means f prime of x has to be a constant, and f double prime of x has to be a linear.
So yeah, if your function's linear, f prime is m and f double prime is 0. But that really proves the converse. Yeah, that doesn't really prove the forward direction.
No, I mean, you can integrate curvature twice, can't you?
Integrate this formula?
Yeah.
Ooh, boy, that's interesting.
Because then, like, at least you know the numerator is just going to get to f of x.
Let's sit on this for a second and just give it a little more than a moment's thought. Is there any type of curve where curvature is always 0? It's not a line.
At least not in the Euclidean space.
Ooh, getting into non-Euclidean geometry. That's exciting.
But at that point, it's still a straight line, isn't it?
How do we feel about cheating?
Yes.
Where do you see text solutions? Right here. Oh, here's the true false. This was question number 10. If they say true, curvature is 0 if and only if big T prime is 0, if and only if big T prime is the 0 vector, but then big T is a constant, which is only true for a straight line. Ooh, that's way more formal than we were saying.
Basically,
It's good, though. It's going back to this thing, right? If curvature is 0, that is 0, which means big T itself is just the 0 vector. Okay. That's cool to learn. All right. Oh, did you see the answer for number 11? No, 11 is false. Let's see what the question is. If the magnitude of R is 1 for all T, then the magnitude of R prime is a constant.
Is the magnitude of something always
Yeah, that's true. Yeah, that's true. The magnitude of something is always a constant. No, it's not. No, it's not. It's always a scalar. It's not always a constant. So wait, when the magnitude is 1, then R prime is a constant. How about a circle? Doesn't a circle violate that? Yeah, if we parameterize a circle with cosine and sine, that's a great circle. Then the magnitude is 1, but R prime is not a constant. R prime is going to be whatever.
It's the
Negative sign.
absolute value.
Say again?
It's the absolute value, right?
No, because R prime is a vector function, so this is magnitude.
Oh yeah. But if you parameterize it with sine and cosine, wouldn't R primes? Couldn't I still do the same thing when I square cosine and sine squared? Would that still be 1?
Yeah, but in that case, it's true.
In that case, it is
all
true.
cases, it's not.
Oh, yeah, you're right. So this is not a counterexample. You're right.
Circle's not a counter.
Circle's not a counterexample.
It said false in the answer.
It did say false. Let's see what they say why. False. If R of t is the position of a moving particle at time t and R of t is 1, then the particle lies in the unit circle or the unit sphere. But this does not mean that the speed must be constant. What? Oh, they've parametrized it differently. Bye. Bye. So they parameterized it with like a rectangular version instead of a. That's odd, isn't it?
Maybe it's even.
Eric, what was your word for that?
Huh. So the way we parameterize the circle affects whether or not speed is constant? Well, that's curious. Okay, I won't put that on a test. Okay, 12. If magnitude of R is 1 for all t, then R prime is orthogonal to R for all t.
Isn't that necessary to like
That's our proof. We proved that, right? 13. The oscillating circle of a curve C at a point has the same tangent vector, normal vector, and curvature as C at that point.
isn't that by definition?
That's definition, yeah. Yeah. Okay. Isn't that where we left off last class, actually? If you look at your notes, weren't we at the beginning of... What did we do?
Oscillating circle.
Yeah. Oscillating circle.
Where did I state the problem, though? Because I don't see it.
Find the oscillating circle.
There.
Oh, right here. This is it, yeah. Okay, then let's pick up from here for a minute. I didn't intend to be 45 minutes in at this point. Oh, well. We had a long... Go outside. Oh. For how long?
15 minutes.
45 minutes.
You just want to go outside and sit? You don't want to do any learning out there?
I'll find the oscillating circle of a tree. I'll do it. Wait, is it that one class like right here? I'll find whatever. I think Mr. Cope is that one class right there.
Yeah. Could we just do it another day?
Oh, you said that last time.
I know, but I never promised the following day I would do it. Okay. I'm gonna object. Yeah, we're gonna work for a bit. I'm sorry. Okay, so I wanted us to find oscillating circle at x equals 2. Okay, so let's see what's happening on this function. I want to factor it for us. Okay, so f of x equals x times 1 minus 1/4 x. This will help us find zeros, and then we can find the maximum and all that. So we've got zeros at x equals 0 and at x equals 4, which means our maximum occurs at 2. So it looks something like this. Let's sub in 2 to the function to see how high that maximum is. So 2 times 1 minus a half. Yeah. So it's 1. So this point right here is at 2 comma 1. So what we're trying to do is we're trying to fit a circle in here that exactly, sorry, it's not supposed to necessarily hit the axis right there, but this circle that I just drew has the same curvature and the same tangent line or tangent vector and the same normal. Okay, so to find the equation of that circle, we need to find the curvature of our parabola at that point. Okay, so f prime of x equals 1 minus 1/2 x, and f double prime of x equals negative 1/2. Remember, we're doing all of this at x equals 2 because that's the x coordinate that I specified at the beginning. So our curvature is the absolute value of negative 1/2 over 1 plus. Okay, now what is f prime at 2? 0, right? 0. So this is 0 squared all to the 3/2. Okay, so that's simple. 1/2 over 1, so our curvature is 1/2. Any questions about the curvature work?
This is what's gonna be on the test, not like 3D.
Yeah, something like this would be on the test. Not a 3D curve, because that would involve a lot of difficulty. I've never done one like that, finding circle of curvature there. Okay, so if that's curvature, radius is 2. Okay, reciprocal, right? So we need to find because the tangent line up here has a slope of 0, we need to find a point that is 2 units away from this tangent point. So that means my drawing really is wrong. It needs to be way down here at the point 2, negative 1. So this should be a circle centered at 2, negative 1 with a radius of 2. Let's build it and then we'll go look at the picture. So x minus 2 squared plus y plus 1 squared equals 4. That's the circle of curvature, or the oscillating circle at that point. Okay, so let's use the calculator to model what we see here. Function was x minus 1/4 x squared. So we had all the features right? The vertex is at 2, 1, zeros are at 0 and 4, all good. Now let's write the equation of the circle. So what did I say it was? X minus 2 squared, y minus plus 1 squared equals 4. Okay, now the thing that shows up should have a matching curvature at that point of tangency. Okay, it worked. Okay, now you've got same tangent, perfectly fits in there, right? Now this one is really nice because the center is along that line tangent to this line, and that line has a slope of 0. So can you imagine it'd be a lot more difficult if I said, now do it right there. Because then there'd be a tangent line like this, and you'd have to be orthogonal to that to get where the center is.
Can we use that for like find the foci?
No, that's not the same place as the focus. No. The center of that circle is not the same as the focus. Because actually, there's commands on here to find focus. Did you know that? If you go to Analyze Graph and go down to Analyze Conics, foci of that thing, so the focus of the parabola is right there, still on the x-axis. Okay. Former students have made me some cool files that like model this, and I want to try and show them to you. Something's wrong. My cursor's not showing up. What's up?
So the radius just like the reciprocal curvature?
Yes. Radius is reciprocal of curvature. What's going on? I can't find my cursor won't. Okay, so what we're trying to do in the derivation I'm going to show you is to find a formula for A of t and also one for A sub n. Okay, so in order to do this, we are going to establish some new notation. We're going to say that a v without a vector hat is the magnitude of velocity, or in other words, the speed. Okay? So that the formula for big T, which we know to be r prime over the magnitude of r prime, can instead be written like this: v over v without a hat. It's just a notation thing that we're going to use to help our work later on. We haven't learned anything new here. R prime is v with a vector hat, and magnitude of r prime is v without one. That's just speed. Okay, I'm going to rearrange that formula so that v is alone. So I'm going to write v with a vector hat equals little v without a vector hat times big T. That's where we're going to start from. Any questions on those few steps? I'm going to differentiate both sides now. ddt of both sides. What's ddt of v? Good. Acceleration. Now look what we're dealing with on the right. This is a scalar function. There'll be an expression with t's in it. This is a vector function. We're going to differentiate it, so we're going to use a product rule. And it's going to go like this. It's going to be v prime big T plus v times big T prime. Okay, we're getting somewhere. Look, we sort of have a coefficient of big T, but we don't yet, unfortunately, have a coefficient of big N. We have a coefficient of big T prime. So let's keep working with something else we know. Curvature is the magnitude of big T prime over the magnitude of r prime. That was one of our curvature formulas that was earlier in the process. And I'm going to rewrite that to say that the magnitude of big T prime equals the curvature times the magnitude of r prime, which is just v, right? So magnitude of big T prime equals kv. Okay, now let's write a formula for big N. Big N is big T prime over the magnitude of big T prime. So big T prime is equal to the magnitude of big T prime times N. Do we see a substitution we can make? See this right here? That's the magnitude of big T prime. So it can go in place of there. So we can say that big T prime is equal to k curvature times v speed times big N. Do we see another substitution we can make? This can go into the acceleration equation. So now that we have something in terms of big N. So we can say acceleration equals the derivative of speed times big T plus v times kvn. Rearrange that a little bit. Now we've got our coefficients. A equals v prime t plus kv squared n. This thing is a sub t, the coefficient that goes in front of the unit tangent vector in this derivation, which is the rate of change of speed. This quantity is a sub n, which is the curvature times speed squared. Okay, we want to turn both of those into something that are, just like over here, we had formulas that were maybe conceptually useful but not practically useful. We want to turn these two into things that are practically useful as well. In other words, we're going to put them in terms of only R. Any questions at this point? Yeah.
Mr. Tom, a really easy question, but conceptually, can we see the original? Would you mind to scroll up a little bit?
Yeah, sure.
Is it like I was thinking like if you project A to the vector and it be like and you can get the constant?
Oh, that's a good question. You mean like take A and project it onto N?
Right.
Okay, so the projection of A onto N would be A dot N over N dot N times N.
Right.
And you're saying that is the component in that direction?
Is it?
I don't know.
Should be.
It should be, but I don't know how to reconcile the two formulas. Well, do we know what N times N is? It's a unit vector, so it would be 1, wouldn't it? So this is A dot N as the coefficient times N. Yeah, I'd have to play with it a little bit. I'm not sure. Yeah. Do you want me to add that to my to-do list?
Only that is a coefficient.
Yeah, it is a coefficient, right? So it probably does work if we have A. Okay, let's do this. This is our expression for A. We're going to dot V with it. V dot A equals V dot V prime T plus KV squared N. Okay, let's do, let me look at my step for a second, make sense of what I was writing there. Oh, I see what I did. Up here, we had a statement that said that, where was it? Right here, that vector V equals non-vector V times T. I'm going to do that here as well. So this is VT dotted with V prime T plus KV squared N. And again, these two are scalars, those two are vectors, so we're going to do some distributive here. We're going to say that that is VT dotted with V prime T plus VT dotted with KV squared N. Which is V prime times T dot T plus KV cubed times T dot N. Just rearranging terms there. Okay, T dot T is the magnitude of T squared, 1. This thing is 1. Okay, T dot N is what? 0. Those are orthogonal, right? So that whole term is 0. So what this leaves us with is this statement. V dot A equals V prime. So V prime equals V dot A over V, which can be thought of as R prime of T dotted with R double prime of T over the magnitude of R prime of T. That looks really familiar, doesn't it? This statement is A sub T. That's a version of A sub T that's easier to use than finding, what was it before? Was it V prime? Right? Yeah, see? V prime, which is the derivative of speed, which we did in our warm-up yesterday, actually, our last class. This one allows us to only know r prime dot r double prime over magnitude of r prime. That's a sub t. A sub n is easier to derive because it was kv squared. Curvature is r prime cross r double prime over the magnitude of r prime cubed. And v squared is the magnitude of r prime squared. Obviously, stuff cancels, and we're left with magnitude of r prime of t crossed r double prime of t all over the magnitude of r prime of t. So this statement is a sub n.
You put like the arrow thing above all of them, like that, all the R's, because some of them have some of them don't.
Or don't.
Like in the,
Oh, the top one, yeah, thanks.
one at the bottom.
Thanks. I missed it there, and missed it there. Thanks. Any others that are wrong? So, given a curve, given r of t, any acceleration of that curve can be broken down into those two components, right? A sub t times t plus a sub n times n, where a sub t and a sub n are those two formulas. One year, I want to skip all the derivations and just get this chapter done in like 2 days. Just like, here's the formula sheet, do the problems, we're done. I don't know if that would be good or bad. Do you have a vote?
Go back to the like,
Yeah.
where there's something with projection.
Projection statement here. Yeah. Is the question really is a dot n the same thing as this statement here? I don't know. I don't know how to show that.
You can change it to t and change it to r.
Mm-hmm.
But that would maybe that the calculator.
Let me write that down.
I would say that one is much easier to manipulate if you're thinking how to find the n.
Mm-hmm.
You do something with like the fact that like for the one that's like A sub t,
Mhm.
it's gonna be like add big T times A.
Mm-hmm. Maybe. Let me play with it. I'll try and do it tomorrow morning. Okay. One more thing from this section is... Oh, wait, questions. I know we haven't really done a problem here, so... Yeah.
So I recognize that there are two like somewhat definitions of multiplication between vectors that being scalar vector or cross product. Like, is there a reason they're coming out like this in kinematic? I'm not sure.
Yeah, I think because AT is direction of motion, same direction. Dot product is really talking about the togetherness of the vectors, whereas cross product is talking about orthogonality of vectors. But I don't know in terms of the kinematics or physics why that's happening. But from the math definitions of those, I think it makes sense. Yeah. Okay, so I want to derive with you, well, maybe we skip the derivation and just state them. They're on your formula sheet. I was thinking about the kinematics equations, right? Which you see at the bottom of the formula sheet if you have it. It's really that any projectile motion in the plane can be expressed with these two components. Can be v naught cosine theta t plus x naught. Those are all scalars. So this would be our x of t function. And then the y of t function would be negative 1/2 gt squared plus v naught sine theta t plus h naught. That thing is y of t. So there's the standard kinematics questions that can be asked about that.
Is that v naught at the end of the x of t?
X naught.
Oh, x.
Like an initial position, but almost always the origin is established to be so that x naught and h naught are 0. right? If your motion starts at the origin, or if you just design your system so it does, this lets x naught be 0 and lets h naught be 0.
That's v0 times cosine of theta times t.
Times t.
Cosine of theta times t.
Yes, it's this and it's this.
Okay.
Good clarification, yeah. Okay, so let's do problems that we find that are related to those from the review.
Is this for the the initial
Mhm,
plus?
mhm. Yep.
You would try that if it's try one the initial t plus 1 half acceleration times squared.
Yeah, just integrate acceleration.
Yeah.
Okay, does anybody remember what exercise we left off on?
13. No, 14.
Find curvature at a point, find equation of oscillating circle. I thought it was before that. Did we do unit tangent, unit normal, and curvature?
Yeah, we did
Like 11?
12. Yeah, we did those.
No, we did not do 12. I know we didn't do 12. Let's do 12 right now. Okay? Let me take a picture of it and move it over to my notes page for us.
Did we say this was defined by P? We did, or T and T prime, P will.
12?
Yeah.
No, because this one doesn't have constant. This is an ellipse.
Oh, wait.
Yeah.
Oh, this is a different 12.
Yeah. Oh, yeah. We're looking at the 12 on the back.
Oh,
All right, find the curvature of the ellipse x equals cosine t and y equals, 3 cosine t and y equals 4 sine t at the points 3, 0 and 0, 4. Okay. Well, we don't have this. This is not a case of y equals f of x, right? We don't have this written as just a function of x. So I think we're going to have to parameterize it as a vector function and then use one of our formulas. So 3 cosine t and 4 sine t, and just treat the last component as 0 since we're in the plane. Okay, let's have you guys walk me through these steps. Who have I not talked to today? Max. Let's use this curvature formula right here. So first, Max, can you please find me r prime?
R prime of t is equal to -3 sine of t, 4 cosine of t.
Good. And then let's have Luke, can you do r double prime?
R double prime of t is -3 cosine t, and -4 sine t,
Good.
and 0.
And 0. Okay. Let's set up a situation where we can do a cross product. And we'll also need the magnitude of r prime. Let's do this one first, okay? Ivan, can you walk me through magnitude of r prime?
So you just get all of the components, right? So
Yeah.
it's basically just to be a squared plus b squared. So you use all the components, square all of them,
Yep.
and then you add them, and then find the square root of that, and then that whole
Cosine squared t.
that whole like thing, right? You just take the cube.
Yeah. Right. Okay. Well, how can we simplify this, you guys?
Sine squared, cosine squared would equal 1.
Yeah, so we're going to have really 9 copies of those. So could I write this as 9 plus 7 cosine squared t? Did I do that right? Yeah. 9 pairs with 7 left over. Okay, so I can write that. I don't know if that helps us really at all. Well, because, right, because you've got sine squared plus cosine squared, you've got 9 copies of that, right? They all make 1. And then you've got 7 of them left over, 7 cosine squareds left over. Okay, so that's, all right, so that's right. And we're going to have to raise that to the third. So this statement is really 9 plus 7 cosine squared t to the 3 halves. That's going to be our denominator. Okay, fine. All right, let's do cross product. I don't want to go to the calculator. I was going to try and do this whole thing by hand. Is that dumb?
It's honorable.
It's honorable. I'm going to try it. Let's do it. Okay, you don't have to write this down if you want. Just chill and can you just make sure I don't make a mistake? Could you do that for me at least? Just watch it. Watch the work instead of truly spacing out. Or yeah, even better. So one of you check me on the calculator and see how we do. Oh, it's not bad. Look, so many of them are 0.
Wait, for these formulas to work, you got to do 2 dimensions. You have to treat the dimensional vectors like they're 3 dimensional.
Yep, you do.
You can't just cross a 2-dimensional vector without the K.
No, there's no such thing as a cross product of 2-dimensional vectors. Okay, no mistakes here, right? It's just 0, 0, 12. The magnitude of which is 12. Sweet. It's probably faster than the calculator. Okay, so this means that curvature is equal to 12 over 9 plus 7 cosine squared t to the 3/2. I think we can do this whole thing without a calculator. We're asked to do this at the point 3, 0, which is when t equals 0, right? Because cosine of 0 is 1, yes, and sine of 0 is 0. Okay, that's good. All right, so let's evaluate k when t is 0. Okay, so that's 12 over 9 plus 7 to the 3/2. 16 to the 3/2. 64. Simplify that. 3 over 16. Well, I'm curious to check the solutions and see if we got that right. The other one's going to be k of pi over 2. 12 over 9 to the 3/2, which is 12 over 27. Yep. Okay, moment of truth. Let's check it. 3/16 and 4/9. Which problem number was this, guys? 12? 12 is 3/16 and 4/9. Cool. Well done. Good. Okay. Oh, shoot, it's late. I'm sorry. That was intense and a lot, and I totally lost track of time.
Go outside, man. We go outside for
Guess so. I guess I should just schedule it. Okay, if it's a nice day, next class we'll take 15 minutes outside, okay? Promise. It's on video. I've been recorded saying it now, okay?
We got proof.
Yep. Having that mouse problem again. It's not showing up. What the heck?